So we've looked at a mass oscillating up and down on a spring, collected position, velocity, and acceleration data. Now we're going to take a look at the equation that appears on the formula sheet, which is that the period for a mass oscillating up and down on a spring is equal to 2 pi times the square root of mass over spring constant. So the following problems are going to be practiced using this equation to either find period, mass, or spring constant. So you'll notice that it's labeled TS sometimes for period of a mass on a spring. But also within the equation you have M, which is mass, over K, which is spring constant. So you have a fraction here, mass on a spring. Now, you may have to solve this equation for mass or spring constant, so we'll first take a look at how to do that. First thing you would want to do is square both sides. When you do that, you're going to get period squared equals 4 pi squared times m over k. You then multiply both sides by k, and you'd get k times period squared equals 4 pi squared m. So from there, you might want to solve for k, in which case k is equal to 4 pi squared m over period squared, or you might want to solve for mass. So you can see that to solve for mass, we'd have to divide both sides by 4 pi squared. So that would give us mass is equal to k times period squared all over 4 pi squared. So there's going to be quite a few problems that use this equation. So you want to make sure that you can read it, identify the variables, and then solve appropriately. So a 0.3 kilogram mass is attached to a spring with a spring constant of 29.4 newtons per meter. So what am I given? Mass is 0.3 kilograms. Spring constant is 29.4 newtons per meter. And I have to solve for period. So here, because we're solving for period, we'll use the original equation, which is already set equal to period. And that should just be a matter of plugging that into your calculator. So you're going to plug in period is equal to 2 times pi times the square root of 0.3 over 29.4, and that's going to give you your period. And it should be 0.63 seconds. And it is 0.63 rounds to 5 seconds. All right. The next one is going to be a similar problem, but we're going to end up finding frequency afterwards. So why don't you try that? And then remember, once you find period, that frequency is just the reciprocal of period. So in order to find frequency, you're just going to be plugging in 1 divided by 0.51 seconds, and that should give you your frequency. In the next one is the first example where we'd have to solve for spring constant. So just in reading over it, I know that my mass is 0.3 kilograms. My period is 0.24 seconds, and it's asked me to find the spring constant. So again, the only equation you would be given is the one for the period on a spring, 2 pi times the square root of m over k. But like we saw above, you can square both sides and solve for period, spring constant. And so you can see from there you get k is equal to 4 pi squared m all over period squared. So if you go ahead and plug that in, you get 4 pi squared times 0.3 all over 0.24 squared. So we'll go ahead and plug that into our calculator. And we get 205.62 newtons per meter. All right. The next one, a 25-gram mass, we need to make sure we pay attention to the units, is attached to a spring. It makes 20 vibrations or 20 oscillations in 4 seconds. Find the spring constant. So the first thing we have to do is convert that mass. So kilo means 1,000. So 25 divided by 1,000 is 0.025 kilograms. We're moving that decimal place 3 spaces to the left. The other thing we need to do is figure out what this is. Recall that we want to start by writing it as a fraction. So we have 20 vibrations in 4 seconds. And remember, we have to ask ourselves a question: where are the seconds? In this case, the seconds are on the bottom, indicating this is in fact a frequency. So I know that frequency and period are reciprocals of one another. I can see that if I reduce this, I get 20 over 4, I get 5 hertz for my frequency. But we'll convert that to period, which is of course going to be the reciprocal. So period is the reciprocal of frequency. So 1/5 is 0.2 seconds. So that will be our period when we plug it in. So again, we're finding spring constant. So you start with the original equation and square it, and then you can solve for K. We did that right here. So I'll bring it down from problem 3. K is equal to 4 pi squared m over period squared. So we'd have 4 pi squared times 0.025 converted to kilograms times, or divided by, 0.2 seconds squared. And we'll plug that into our calculator, and we will get, when we do that, we get 24.67, which I rounded to 0.7, and that's in newtons per meter. All right, and then 5 is another practice question where we have to find the spring constant. So we'll do that a similar way. Remember that if we do need to solve for mass, you are going to be using this form of the equation right here. M is equal to K times period squared divided by 4 pi squared. One thing to remember is that when you type this in, if you're off by a factor of 10, it's because that you forgot parentheses around the denominator. Or probably an easier way is not to use parentheses and just do K times period squared divided by 4 divided by pi squared. So let's take a look at our conceptual questions. So if the mass quadruples, the period does what? So as you can see, we are back to the rule of ones. So what happens to period? So let's write down the period equation. Period for a mass on a spring is equal to 2 pi times the square root of m over k. So rule of ones, we plug in a 1 for any variable that stays the same, and we plug in the number for how it changes if it does change. So for example, if it doubles, we'll put in a 2, quadruples, we put in a 4, half, we put in 1/2, etc. So in this case, it says the mass quadruples. What happens to the period? So in the first one, we have 2 and pi are constants. Inside of the square root, it tells me that the mass quadruples. Does not mention any change to the spring constant. So I have the square root of 4. Square root of 4 is 2 times. This is going to double. Okay. Now, the next one says, if the spring constant is quartered, what happens to the period? So let's take a look at that. Period on a spring, 2 pi times the square root of m over k. 2 and pi are again constants. Our mass is not referenced, so I put in a 1. But spring constant k is quartered, so I'm going to put in a 1/4. So 1 divided by 1/4 is 4. And the square root of 4 is 2, so again this is going to double. All right. The next one, mass doubles. What's going to happen to frequency? So what I would recommend we do is we figure out what happens to period, and then just take the reciprocal to figure out what happens to frequency. So again, for number 3, we'll plug it into this equation. And when I do that, it says mass doubles. Nothing about spring constant. So what's going to happen to period? It's going to increase by a factor of √2. But recall that frequency is 1 over period. So if period increases by a factor of √2, frequency is going to decrease by a factor of √2. Or if you wanted to get rid of the radical in the denominator, √2 over 2. So if the mass doubles, the frequency will be 1 over √2 times the original amount. And the last one, if the spring constant increases 9 times, what happens to frequency? 2 pi m over k. Spring constant increases by a factor of 9. So the rule of ones tells me mass is the same. Spring constant increases by a factor of 9. Square root of 1/9 is going to be 1/3. So period is going to increase by a factor of 1/3, but frequency and period are reciprocals. So if period is 1/3 of the original amount, you can see that 1 divided by 1/3 is going to be 3 times the original amount. So when my period changes by a factor of 1/3, my frequency is going to triple. So that is the mass on a spring equation. Period is equal to 2 pi times the square root of m over k.